Hi, this is Gary Auden, and I'm bringing you an EduCast. Can you hear me now in every room? Build a great unified communications experience. With me today is Revo Labs, and representing Revo Labs is Denise Iverson, Director of User Experience and Product Marketing. But as we always do, we'll talk about what we're going to talk about. And one of the first points we want to make here is you just can't buy a single product that fits every room and every arrangement. You need different kinds of audio conferencing products. The biggest, highest specification is not always the best. So we're going to talk about what you should look for: the pickup, the playback, and the processing, right? When you have all this right, there's still more to consider. So let's start off, Denise, with your first slide here. These three stages, three parts of audio in UC.
Right, thanks, Gary. So, yeah, what we want to do today is really just kind of break things down sort of maybe scientifically in terms of technology and just give us sort of a 101 of what's going on with audio. And so we think of audio really in three parts. There's the capture, the transmission, and the reproduction. So the capture starts when something is spoken from the mouth. It moves through the room and then makes its way to the microphone. At that point, there's some encoding, transmission across the network, some decoding, and then it comes out the speaker, and again, it's going to move through the room before it reaches the ear. So what we really want to talk about today is the area that Revo Labs focuses on, which is how does the room affect that capture, and how can we do things with the microphone to create the best capture that then, once it's transmitted, comes out through the speaker in a way that can be heard and understood, and then how does the room, again, affect that before it reaches the ear.
I don't think a lot of people understand the environments we have to work in here, and your slide here, Key Facts, presents a number of things we have to think about, because not all conference rooms are going to be equally as quiet or equally as suitable for a conference call.
Right, exactly. So yeah, here's all this really is for, is to give us some reference points as we kind of move through the rest of the discussion today. And so in the top left, I kind of give you some basic measurements of speech, right? So speech is measured in terms of sound pressure levels. We refer to that in decibels. And normal speech at about 3 feet away, if someone's speaking to you, that will reach your ear at a pressure level of about 60 dB. Somebody speaking a little quieter at that same distance is going to hit you at about 50 dB, and somebody yelling at that distance is going to be more like 78 dB. So that matters as you move over to the right column, where we talk about some of the ambient noise that is just present in rooms. So this can be like HVAC systems, electronics, people moving around, you know, talking in the background. These kinds of things create what we call an ambient noise in rooms. And so if you look at the standard meeting room, the ambient noise probably runs around 40 to 50 dB. That's fine in that room if somebody's speaking to you at 3 feet away at 60 dB. When somebody gets down to that quieter speech at 3 feet away, you could begin to have trouble hearing them. When you move into things like these open floor plans that are becoming quite popular today, you can immediately begin to see how we could be struggling to hear even at a normal tone of, level of speech. And even if you look at classrooms, this gets a little bit disturbing when you start to think about the average classroom and those students sitting in the very back of the room, and how a teacher speaking even in an elevated voice could just become nothing by the time it reaches the back of the room. So we'll talk a little bit more about how those things play together. And then on the left side back at the bottom, we talk a little bit about hearing damage. And so what's interesting here is the surprisingly low level of sound pressure level that can actually begin to create a risk factor for hearing damage. 85 dB, that is really the pressure level that you would experience if you were sitting in an airplane right behind the engine. So if you can imagine an international flight, doing that multiple times, you're actually creating some level of exposure risk for hearing damage. 100 dB, that would be like a rock concert. Just 15 minutes in, you do that on a regular basis, you're definitely exposing yourself to hearing damage. So surprisingly low levels of pressure level can create risk factors for hearing.
Let's move into that word pressure level. And what you're pointing out here, I believe, is there's a relationship between that pressure level and how far you are away.
Absolutely. So pressure level is related to distance. So the further away you get from the source of the sound, the pressure level diminishes across that distance. And it's a logarithmic function, so it's something that can be calculated once you know a reference pressure level, and once you know a reference distance, you can you can calculate the pressure level at another distance.
When I look at this, I don't live with a lot of formulas. Could you relate this to something a little closer to what I can understand?
Right, exactly. So what really matters here is not so much the complexity of that formula, but sort of the rule of thumb by which we can operate now, and that is every time you double the distance from the source of the sound, the pressure level drops by 6 dB. So moving from 3 feet to 6 feet, you're going to drop that pressure level by 6 dB. And we'll use that again as a reference point as we continue the conversation today.
I think the next slide has a good illustration of what you're talking about.
Exactly. So here we try to show what happens when someone speaks at a half a meter away. That sound pressure is going to hit your ear at 65 dB. As you move further away, double that distance, you can see it drops by the 6 dB. And as you get to another doubling of that distance, 2 meters away, it drops by another 6 dB. Now you can imagine at that distance, and we've all experienced this, that sound coming to you actually is much quieter at a perceptive level. It sounds more like somebody speaking quietly. As we move further to the right, you can see I didn't actually double the distance here, and this is just to reinforce the point that this is a logarithmic function. So it's not, we didn't go down by 6 dB because that would have been 4 meters away. But even at 3 dB, it's not half of 6, right? It's a logarithmic calculation of the distance between 2 meters and 4 meters and the dropping of the decibel levels. Also important to talk about here is that this is in free space. So this would be in an environment where there are no reverberations, nothing that would reflect that sound wave and cause any kind of an echo or playback of that sound.
I think that's great, but the other part that I get concerned about is, do I understand what's being said?
So being able to hear, of course, is important, but more important is once we hear it, can we understand what's being said? And so that's where speech transmission index comes into play. STI is just a measurement that actually predicts the likelihood that you're going to comprehend what's being said in a particular environment. So this takes into account those things like reverberation that I just talked about. And the goal here is to really be in that good to excellent range. So you can see what they've done with this measurement, and these tests can be done and repeated, and there are tools that can help you do it in any kind of an environment you have. But what we're doing is measuring how well will you understand syllables, words, and sentences. And we all know that when you hear something in the context of a sentence, you're most likely going to comprehend it more accurately than if you heard individual syllables or even words. So we're really trying to get into that good to excellent range when we try to measure the STI in a particular environment.
Yeah, your next slide is titled The Real World, but could you interpret this for us, please?
Yeah, absolutely. So the point is, yeah, we talked about STI and we understand what that means, but how does it really apply to what we're doing? So this was a study done in classrooms. We're trying to evaluate factors that might be affecting the ability for students to learn in typical educational environments. And so what you want to focus on here is sort of that green area, which translates back to the previous slide, that green, the good to excellent. And what they've done is they tested single syllable words and the ability for students to accurately understand what was being said. And you can see in a quiet room where there's no noise floor at all, none of that ambient noise, the interpretation is excellent, right, at a 0 reverberation. When you move up to some reverberation, like 0.4 seconds, it's still great. When you get 1.2 seconds of reverberation time, it drops dramatically. Reverberation time is the amount of time it takes for that pressure level to decay. So 1.2 seconds in a very large room is a really good reverberation time. In a small room, it's not very good at all. And when you think about a classroom, what they saw right there is that there was a significant decrease in the ability to understand the words being spoken. Now, as you move down, the plus 12 dB and the plus 6 dB, this is the signal to noise ratio. So this is the voice compared to the ambient noise being 12 decibels above or 6 decibels above. And we still sort of stay in that green range even as we begin to get some reverberation. But you can see as soon as that voice starts to get closer to that noise level, students don't have a chance of hearing anything, particularly in a classroom where there's 4 walls and lots of things for sound to bounce off of. The ability to hear things intelligibly goes way down. So this has a correlation to what happens in our conference rooms as well.
So now we get to what does this all mean, and let's return back to those 3 stages, 3 parts of UC conference audio.
Right, exactly. So what we want to talk about is we want to apply this now to what we can do in terms of capturing sound in a conference room and replaying that sound back. And those are things that we, Revo Labs, being in the business of creating audio conferencing equipment, will take into account. But then there are also things that are more general, such as the room and the reverberations of the room, that will have an impact on our ability to maximize intelligibility, as well as make that processing that we do to get better capture and reproduction much easier. And we can talk as we move through about the games that we can kind of play with processing technology, but then the side effects that some of those games have when you try to push them to the extreme.
I'd like to just say on the slide another moment. What it sounds like you're saying is the conference equipment has to actually compensate for the variations of the room and the environment it's working in. Is that correct?
That's absolutely correct. So it's compensating for the room, the environment, the reverberations, other acoustics. It's also compensating for the way in which people are positioned around the conferencing equipment. Like how big is that room and how far away are the different users who are trying to hear and speak into that microphone.
Let's dive into those 3 points and start off with capture.
Okay, so what we want to do here is we're just setting up sort of a basic room scenario. So I've drawn the red line, which is just emulating a standard noise floor in basically a conference room. We put it at 48 dB. And then we have the green line, which is the speech, the pressure level of the speech. And so, like we saw on the very first slide, at 3 feet, we have it right around 60 dB. And then as we saw that logarithmic function, it's going to taper off and be less and less pressure as it gets further and further away, doubling going down by 6 dB every time it doubles. And then you've got the 2 blue lines, which correlate to, on the slide where we talked about the classroom, where 6 dB and 12 dB above the noise floor created the best environment for intelligibility, right? We had really good in that upper green level of intelligibility. So what you've done here when you slid that down is this is sort of one of those things we can do with processing. We can, with technology, sort of reduce that noise floor, bring that down. In this case, we show it coming down by about 10 dB. And when we do that, we bring down then that 6 dB above and 12 dB above pushes lower. And then that voice can now be more intelligible at a farther distance away. So now you can see it like 12 to, 17, 18 feet away. That's still a very intelligible voice that we can pick up. We can pick up that voice with great intelligibility. Now the other thing we can do is automatic gain control, which means as that logarithmic function, that voice was continuing to taper off as we approach 20 feet and get below the intelligibility level, we can actually boost the pressure, right, that we're getting from that distance so that people up to 20 feet away still sound as good as the people at 12 feet away. The other thing we can do is on the front end is we can lower the pressure level of those voices that are coming in very close to the microphone. So we're sort of normalizing those, right, and tapering off so we don't have those big spikes and low levels of voices from close by and far away. The problem with that, however, is that once you start to do that and you're picking up sound from up to 20 feet away, we can't necessarily tell anymore if that's something that is part of the conversation in the room or perhaps something going on outside of the room, people walking by who are talking. So you get some artifacts from playing these games, particularly when you get those long pickup ranges. So to the point here, too much mic pickup isn't necessarily a good thing. And the closer we can get microphones to the people in the room who are speaking, the less processing and the fewer games we need to play, which lead to some of those bad experiences.
Now, we've been talking about the near end, my end. Now we're going to need to talk about the far end. And is there a similar conversation about that?
There is a similar conversation, except that we can't play as many games, right? About the only thing we can do when we reproduce that sound, when we play it back through the speaker, is we can boost the volume on it. So As we begin to shift the volume, certainly people who are further and further away from that speaker are going to be able to hear and get better intelligibility of what they're hearing. But look what's happening to those people who are much closer. Those people 3 feet away are now feeling like they're being shouted at. So if you sit in an hour-long meeting like that, it's like experiencing being yelled at for an hour. That's very tiring. It creates a lot of fatigue, frustration. It even can approach levels of hearing damage, right, if you try to boost that too far out. So the lesson here is, again, just trying to get the speakers close enough to the individuals in the meeting such that it's at a comfortable volume that makes it a very intelligible sound, but not so much that it creates a tiring environment to work in.
One of the things that I've been experiencing is in conference rooms, the rooms are always different shapes, the tables are different shapes, and that seems to imply that the conferencing units have to be somewhat different for the room, that arrangement. Is that correct?
Yes, exactly. That's what we've been trying to point out here, is that there is a lot of factors at play here, and at the end of the day, you really do need to choose the conferencing equipment that best suits the environment that you're using. So what we're trying to point out here is you might have a long rectangular table, and the goal really always needs to be to try and put a microphone and speaker equidistant from every participant in the room. That way, the conferencing unit can be tuned so that it's got an even pickup range and an even playback range that's comfortable for everyone and maximizes that intelligibility. So this is an example of a long table rather than maybe just putting 2 conferencing units equidistant apart on this table, where you might have some people who are up to 6, 7 feet away and others who are 3 or 4 feet away, in which case we have to do more playing around with that processing, potentially get some of those weird artifacts that create a bad experience. Now we're creating something where all of these units can behave somewhat the same way. The processing can be done in a way to optimize what's happening without creating a bad experience.
If I have a square table, does that affect the unit I buy?
It absolutely does. So here we have 2 examples of square tables, right? So again, we just have one conferencing unit in the center of each of these tables. That is perfectly acceptable, but these 2 conferencing units would not be the same one. The one on the left would be more optimized for a much shorter pickup and playback range, whereas the one on the right is going to have a much wider playback and pickup range, but it's going to be tuned such that it's not doing too much pickup outside of the room, and it's not having to do a lot of those games with gain control, right, because everyone's voices should be coming in at about an equidistant. But these 2 units are not the same, even though it's a similar setup.
I know there's always more to learn. Do we have some more to discuss?
Well, the other things I would talk about is we are in the business of audio conferencing for sure. And while we believe and have stated that it's going to be very hard to have a meeting of any sort without audio, video is a huge aspect of the way we communicate as well. So I just wanted to point out a couple things that we see time and again. So this study here has been quoted many, many times by conferencing and communications providers. The problem is that it's often misquoted as trying to say that within communication, 93% of communication is not about the words we say. It's about the body language. It's about the tone of voice. That's not really what this study was about. This study was about the discrepancy between the words you say and what your nonverbal cues are conveying, and which of those nonverbal cues are you most likely to trust to properly comprehend what's being said. So as an example, if I were talking to you about love and I'm using words that show, a very positive perception of love and positive emotion, but in the meantime, my fists are clenched up and I've got, a sharp bite to my tongue, what are you going to interpret from what I'm saying? Are you going to believe the words, or are you going to believe what I'm communicating based on my nonverbal cues? So this is where the visual and the quality of the audio together have a whole lot more impact than just the words themselves.
You have a word on the next page, schizophonia. Would you help us with that?
Yes, so schizophonia is this idea that the source of the sound that you're hearing does not match the environment you're in. And we experience this all the time. You and I are experiencing this right now, Gary, because we're talking by audio. So I can't see you in your environment, and you can't see me. And even though I'm not consciously aware of it, I do hold in my mind some images of the environment you're in, what it looks like, you know, how you're existing in that environment, whatever it might be. That means I'm using some of my brain power towards that, which means I may not be listening and hearing everything you're saying, despite the fact that I believe I'm wholly focused on just you and what you're saying to me. So it's sort of that disconnect between the environment you're in and the sounds you're hearing. So again, it just makes the case for how important video can be as a layer in the communication.
Would you summarize what we've talked about for me, please?
Sure, absolutely. So I don't think for us to say that keeping reverberation low as possible in a room and ambient noise down is anything surprising to people. It makes perfect sense that you would want to do that. But what may not be so obvious is that, again, some of the biggest or best specifications don't necessarily mean you're going to get a better experience. So like we saw, very long microphone pickup ranges could be great if you want to pick up people at a far distance in the room, but what is that going to mean in terms of sounds that are happening outside of the room and people who are sitting close to the microphone? On the flip side, same thing with the speaker. What kind of experience are you creating when you try and make one size fit all and just play games with the processing? And then ultimately, like we just talked about, it's not all about audio. There is more to it. Audio is significantly important. You want it to be great, but it's better with video.
I think it's important for the audience to note that you have a whole range of products to fit these environments.
Yeah, we do. So our portfolio is very focused, again, on audio conferencing and having the right product to fit the right environment for the right use case. So we have everything that moves you from a very portable, ad hoc type of environment in an office all the way through to the largest and best appointed of boardrooms, auditoriums, classrooms for education facilities. So just like we've talked about today, it's really about choosing the right product to the right space, and we have everything that we can do to offer that.
I'd like to point out to people that there's contact information available here, and there's an interesting white paper called Sound Matters. And I'd like to thank Denise for today and the education she's provided for us. Thank you, Denise.
Thank you, Gary.